Hi, I'm Lexi, and I'll be going over the solutions to practice exam 1. Okay, so for the first problem, it says in a recent campus-wide wellness survey, 213 out of 1,245 students admitted to dancing like there's no tomorrow at least once during a finals week. And we want to construct a 95% confidence interval for the true proportion of students who unleash their inner dance machine under academic stress. And then we have our answer choices here. So we are looking to solve proportions with one population. So we can pull up our formula sheet, and we'll see over here that our confidence interval for one population is over here, so that's our formula. And then we can use this on our exam. So we have our population here, so this is our sample proportion, and we want to find our confidence interval, which is a 95% confidence interval, which means our alpha is equal to 1 minus 0.95, which is 0.05. So now we can calculate our confidence interval. So our p-hat is 213 over 1,245, and 245, and that should be 0.17108. Now we can construct our confidence interval. So we have our p-hat plus or minus, and then we have our z of 0.05 divided by 2, so that's 0.025. And we can look on our z table for this. So 0.025. So since we're looking for the right side, what we can look for is 1 minus 0.025, which is 0.975. And we'll see that it is over here. So that gives us our z value of 1.96. And then we can just plug that in over here. Times our p-value, and then 1 minus our p-value. Well, this isn't our p-value, this is our p-hat. So our p-hat and then 1 minus our p-hat, and divided by our sample size n, which is 1,245. So that's over here, that's our n. And then all of this is in our square root. And then if we solve that, times our square root of 0.17108 times 1 minus 0.17108 divided by 1, 2, 4, 5. And we get plus or minus our p hat plus or minus 0.0209 2, and then we can add and subtract that from our p hat. So that's 7108. So then we get our confidence interval of 0.15 0 to 0.19 2. And that's our confidence interval. And then we see that's this answer over here. So we know that our answer is A. Now for our next problems, we have a group of statistics students hypothesize that walking an exceptionally cute dog increases the number of friendly interactions they have in the park. And so they want to estimate the mean number of friendly interactions per walk with a margin of error of 1.5 interactions at a 95% confidence level. And based on the previous dog walking escapades, they estimate that the standard deviation of friendly interactions is around 6. And so how many walks with the exceptionally cute dog should they observe to ensure the desired margin of error? So here we want to estimate our mean number of friendly interactions per walk, and then we want our margin of error of 1.5 interactions, and we want a 95% confidence interval. So our alpha value will be 0.05, since that's 1 minus 0.95. And then we have our estimation of our standard deviation of friendly interactions. So that's around 6. So that's our standard deviation. And now we want to find our confidence interval. So we can look at our formula sheets. We want to use the formula for finding our mean with a known standard deviation. So if we just look at our table over here, so we have our two-sided confidence interval for our known standard deviation, and that is this formula right over here, and that's what we can use. And we'll take our formula, so I can write it down over here again. So we have x bar, essentially it's x bar plus or minus our z alpha divided by 2 times the standard deviation over square root of n. And when we break this down, this is the value that we're estimating, and then this is our estimation for our margin of error. So this is our error over here. And so this is what we're going to set equal to our margin of error that we're looking for, which is 1.5. And so we can set this equal to 1.5 and then solve for our n. And then that's how many walks that we need. So we have 1.5 equals our z, like that. And then we can calculate our z. So it's z alpha divided by 2, so that's our z value with alpha value of 0.025, and we had that alpha value earlier, so we saw from the z table that it's 1.96, and so now we can just plug this in, and then we have 1.5 equals 1.96 times our standard deviation, which they give over here is 6, and then divided by the square root of n, which is what we're solving for, and we can just solve this like normal. So we can divide both sides by 1.96. I'm just gonna write it out, and then we have 6 over square root of n, and then we can multiply both sides by our square root of n to cancel it out over here, and then we can multiply both sides by our 1.96 over 1.5 to cancel it out over here. .96 over 1.5. And so then we have our square root of n is equal to 6 times our 1.96 divided by 1.5, and then we can square both sides, and then we get n equals, and then I can just plug this into a calculator, and we get 1.96 divided by 1.5, and then all of this is squared. And that should be equal to around 61.47, and then we can just round that up, so that's around 62. And that should be our n, and so that's this value over here. And note that we want to round up, because if we round down, then our sample size will be slightly too small, and so we'll just be slightly under, we'll have a slightly higher margin of error, and we want to stay within that margin of error, so that's why we round up. Yeah. So that's our answer for number 2. And for our next questions, we have this problem over here. So studies have shown that regular physical exercise significantly reduces symptoms of anxiety and stress. And a mental health research institute collected data on the average reduction in anxiety scores measured on a standard scale after a consistent 6-week exercise program. And a random sample of 9 participants with a sample standard deviation of S equals 1.487 was taken, and the reductions in anxiety score were the following, listed over here. And we will use the data to make inferences about our average reduction of anxiety scores due to the exercise program for our population. And so suppose a 95% confidence interval was calculated to be from 6.5 to 9.0, and we want to determine if each of the following interpretations is true or false. So our first interpretation is asking 95% of all individuals who participate in this exercise program will have a reduction of anxiety between 6.5 and 9.0 points. So this is false. So our confidence interval doesn't determine that every 95% of our participants will have this. We are just 95% confident that the true proportion, the true mean for our population lies within our interval. So we're 95% confident that the true proportion lies in, or true mean lies within that, But that doesn't mean that 95% of our intervals, of our people who participate in the exercise, will have a reduction of anxiety there. That's just not how we interpret a confidence interval. So this is false. And then we are 95% confident that the average reduction in anxiety scores due to the exercise program is between 6.5 and 9.0 points. And yes, that is true. That is how we interpret our confidence interval. We are 95% confident that our interval contains the value we're estimating. In this case is the true population mean. So this is true. And then we are 95% confident that the average reduction of anxiety scores for 9 participants in the sample is between 6.5 and 9.0 points. And so this is false because our confidence interval is for our population, our true population mean, but that doesn't mean that our sample mean will lie within these. And also, since our sample size is so small, the chances are that we probably will have outliers in our sample, and so we can't be confident. This is not what our interval tells us, so this is false. And then what is a 90% confidence interval for mu? And so we can calculate that. So our 90% confidence interval, that means our alpha is 1 minus 0.9, which is 0.1. And then let's see what information we have. So we have our random sample of 9 participants, so this is our N. And then we have our sample standard deviation, so that's our S was taken, and we have our anxiety scores here. And so we can find the mean from this. You can calculate that by just adding them all together. And then dividing by the number of elements. Okay, so we have 8.2, and then 9.5, and then we have 6.8, 7.9, 5.6, 10.1, 6.3, 7.5, and 8.9. And so those are our values. Just double check that I got them right. And then our mean is x bar, and so that's our sample mean, and that should be around 7.867. And then now we want to find our confidence interval. So we aren't given our population standard deviation, so we have to solve with an unknown standard deviation. And so we can look at our formula sheet over here, and so we can look at our confidence interval for our unknown standard deviation, and so that's over here. So we can use this formula. For our two-sided confidence interval, and then we can just solve for our values. So we need to find our t value. So our t is alpha divided by 2, and then with our degrees of freedom of n minus 1. So this is t, and then our alpha divided by 2, so that is 0.05. And then our sample size. So we have our n over here, which is 9. So n minus 1, 9 minus 1 is 8. And then we can pull this up on our table. So we have 0.05 and 8. So we can look at our t-distribution table. And then we look at our degrees of freedom. So we have 8 degrees of freedom. And we want to look at 0.05. And that's over here, since that's 0.05. And then we have our t-value, which is 1.860. So we can use that. It's 1.860. And now we can just use our formula. So we have x bar plus or minus our t times our s divided by square root of n. And so we can just plug in our values now. So 7.867 is our sample mean. So then plus or minus our t value, so that's 1.860, and then times our standard deviation, and that's 1.487. So we have 1.487, and then we have square root of 9. And if we solve for this, that's 1.860 times 1.487 divided by our square root of 9, which is 3. So that would be equal to our 7.867 plus or minus 0.92194. And then we can calculate our confidence interval, which should be so that should be 6.945 to 8.789. And then we can look 6.945 to 8.789. So that is our answer D over here. And so that would be our correct answer for calculating our confidence interval. Okay, and then for the next question, consider the following 3 statements about confidence intervals. And so our first statement is higher confidence level is wider interval. And then our second statement is larger sample size, narrower interval. And then if you want a high confidence, for our third statement is if you want a high confidence level but not a wide interval, decrease the sample size. And then we're looking for the truthfulness of these statements. And so if we just look at our formula for our previous one, we can see that so our larger confidence level does mean a higher confidence level means a wider interval. So if you look at our tables over here, as our values get as our alpha value gets smaller, our t value gets larger, and then we see the same thing for our z values. So as our alpha values get smaller, our z value gets larger, so this is on the left side, so we can ignore the negative. So we see that as our confidence goes up, we see that our statistic, which is z or t or whatnot, tends to, as our alpha goes lower, this goes up, and when our alpha goes lower, our confidence interval goes up. I hope that made sense. So we know that this is true. And then larger sample size is narrower interval. So we can see in our formula back here, we see that we're dividing by our sample size. So that means larger sample size makes our interval narrower. So that's true. And it says if you want a high confidence level, but not a wide interval, decrease the sample size. And so we already established that a larger sample size makes a narrow interval, and so decreasing it would make our interval wider. So this is false. And so our answer should be C, which is that 1 and 2 are true, but 3 is false. Okay, so for number 8, we have a new manufacturing process for a certain type of component results in a mean lifetime of 800 hours with a standard deviation of 40 hours. And we want to test our hypothesis that mu equals 800 against our alternate that mu is less than 800. And we have a random sample of 36 components that are tested, and the critical region is defined to be our x bar is less than 790, and we want to evaluate the probability of our type 2 error for mu equals 785. And so the first thing we want to do, since we're trying to calculate our type 2 error for estimating our mean, is we want to calculate our z-score. So if you recall, our z-score is calculated as x minus mu divided by our standard deviation. But since we're trying to calculate our type 2 error, we want to use our sample standard deviation rather than our population standard deviation. So here is our population standard deviation. And if you recall, we can find our sample standard deviation, also called our standard error, as S is equal to our standard deviation divided by the square root of n. So we can calculate that right now, right here, and then that's 40 divided by 36 components, so square root of 36, and then that should be 6.67, and then now we can plug this in. So our x value is going to be our 790 over here, since that's the bound of our critical region. So we're looking for if it's less than this x value of 790. And then we have our mean here, which is 785. And so we can just plug that in. So we have 790 minus 785. And we divide it by 6.67. And then if we calculate that, 75, so then that's 5 divided by 6.67. So that is around 0.75. Now that we have our z-score, we can calculate our standard or type 2 error. So our type 2 error would be equal to our type 2 error would be equal to our probability of our z-score And then since we're looking for if it's less than, we do less than, since we're looking for less than here, we would want to do greater than or equal to our z value. So basically our type error formula is do not reject, given that our mu is 785 and this is equal to the probability that our x bar is greater than or equal to 790, given that mu is 785, and so then we would just find the probability that our z is greater than or equal to our z-score, so that's 0.75, and then we can pull this up on our table. So we have our z table over here. So we need to find 0.75. And since this is our z value, we have 0.75, and that's this over here. And then our z table shows less than, so since we're doing greater than, we just want to do 1 minus this value. So it would be 1 minus our 0.7734. And that would be equal to 0.2266. And so that is our type 2 error probability. And so that should be A over here. Okay, so for the next problem, we have a random sample of 25 observations from a normal population yields a sample variance of 16.8. And we want to construct a 95% confidence interval for the population variance. So then we can look through our formula sheet, and we should have our formula over here. So we're trying to find a confidence interval for our variance, and so we have this formula over here, which we can use. So let's go back. And so what we need is our values. We have our n value, which is 25, and we have our sample variance, which is 16.8, and then we need to calculate our chi-square value. So we're constructing a 95% confidence interval, so that means our alpha is 1 minus 0.95, which is equal to 0.05. And we want to calculate our two chi-square values. So we have chi-square with our alpha divided by 2, and then our degrees of freedom is n minus 1. So we have our alpha here is 0.025, and our degrees of freedom is n, so 25 minus 1, so that's 24. And then we also need to calculate another value, which is our chi-square value of 1 minus our alpha divided by 2, so that would be 1 minus 0.25, which should be 0.025, which should be 0.975, and our same degrees of freedom. And so now we can look on our chi-square table to find these values. So if we go all the way to our chi-square distribution, and we can see our alpha values on the top. And so for our first one, we want to look for 0.025, so that's over here. And then we have our 24 degrees of freedom. And if we look, we have our value right over here. So that's 39.364. So that's 39.364. And then we want to find our other chi-square value. So that would be for 0.975, which is over here. And then we have our 24 degrees of freedom. So that should be this over here. So that's 12.401. And so now that we have our chi-square values, we can use our formula that I showed earlier. So for our confidence interval, we would want to have our n-1 times our variance divided by our chi-square. So this would be our first chi-square value, so that's 0.025, 24, and we have our second one, which is n-1 s squared, and then our chi-square value, which is 0.97, or our chi-square with our alpha of 0.975, 24 degrees of freedom. And then we just plug this all in, so we have 24 times 16.8 divided by 39.364, and then we have 24 times our standard deviation, again 16, or our variance, which is 16.8, and we divide it by our other chi-square value over here, which is 12.401, and then we can just solve these, which should give us, let's see, and this would be equal to 10.243, and for our other side we have 12.401, and then that would be 32.514, and so that should be our value, our confidence interval, and then we see that right here, so that's this answer over here, so our answer is A. Then for our next problem, we have a manufacturing process requires that the variance in component lengths to be no more than 0.04 millimeters, and we have a sample of 20 components yields a sample variance of 0.0625 millimeters squared, and we want to test our hypothesis that our variance is 0.04 against our alternate, which is variance is greater than 0.04 at a 5% significance level. And we have our answer choices over here. So since we're testing our variance, we want to use our variance formula in our formula sheet. So if we look over here, if we're testing for that, we have our chi-square value over here, and we can use this value, or this formula. So we can calculate our chi-square, and we have our sample size, which is 20, and then we have our sample variance of 0.0625, so we can just plug that all in, and we have so we have 19 times our sample variance, which is 0.04 or 0.0625, and we divide that by our variance that we're testing against, so that's 0.04, and then we get that as our values. So now we can just plug that all in, and we can get our chi-square value of 29. Oh, I missed a 0 here, so it's 0.625. So our chi-square value is 29.6875, and we're testing at a 5% significance level, and we're doing a one-tailed test. So this is that we're testing that our variance is greater than 0.04, and so since it's a one-tailed test, we can solve using our one-tailed test p-value. So our p-value is going to be equal to probability that our chi-square value is greater than our 29.6875, and we can look that up on our chi-square table. And and our degrees of freedom should be 24, or sorry, not 24, it should be 19. So keep that in mind when we look at our table. And so we have our 19 degrees of freedom, and then don't see your 29 yet. And let's look over here. So 19 degrees of freedom, and our 29 is between these two values, so it's between 0.05 and 0.1 for our alpha values. So we know it's greater than 0.05. So, and since we're testing at the 5% significance level, this is less than our alpha value, and so, sorry, this is greater than our alpha value, so we fail to reject our null hypothesis. So we have our do not reject, and our test statistic is 29.69. So it's this answer over here. We could also calculate our critical value, which would be 30.14, but we don't need to. So this is our answer, which is D. And then for our next questions, we have a car manufacturer claims that our new model gets 40 miles per gallon on the highway, and our consumer group tests 16 cars and finds the mean of 38.5 miles per gallon with a standard deviation of 3.2 miles per gallon. And we want to test if our true mean is less than 40 miles per gallon at a significance value of 0.05. And so we need to calculate our test statistic first. So since we're calculating our mean, and let's see, so we only have our sample standard deviation over here, and we're only testing 16 cars, so that means we want to use a t-test. So we can look at our table here, our formula sheet, and so we have our t-test with our unknown standard deviation for our population, and so we can use this formula over here. And so we have, that is x bar minus mu 0 divided by s divided by square root of n, and our degrees of freedom is n minus 1. And so in this case we have 16 cars, so it's 15 is our degrees of freedom. And then this is our mu, and our sample mean x bar is 38.5, and our standard deviation here, which is our sample standard deviation, and that is 3.2, and then we have our n again, which is 16 cars. So we can plug all of that in, and we get 38.5 minus 40 divided by our 3.2 divided by our square root of 16, which is our n. And then if you plug that into a calculator, 38.5 minus 40 divided by 3.2 divided by square root of 16 is 4. So then you should get negative 1.875. And then that's around negative 1.88. So that our correct answer should be B for our test statistic. So now we need to calculate our p-value to test whether or not to reject our null hypothesis. So first we need to see what our alternate hypothesis is. So in this case, our alternate hypothesis is that our true mean is less than 40 miles per gallon. And so now we can calculate our p-value, which is going to be equal to the probability of our t being greater than our negative t statistic, and that would be greater than our test statistic, so that's 1.875. And then we can pull up our t-table. So have this over here, and our degrees of freedom again is 15. So we can look at here and we see 1.875 is between these two values, so it's less than 0.05. And this is greater than, so this is the right side. So now we can say that it is less than 0.05. It's between those values. And then since we're using a significance value of 0.05, since it's less than, we reject our null hypothesis. And so we have our range here. So yes, our p-value as we can see from our table over here, is between 0.025 and 0.05. So we can write it like this. So we have that right here, so 0.025, 0.05, and we reject our null hypothesis, and so our correct answer would be B. And okay, for this problem, a study compares two diets for weight loss. Group A with diet 1 has 10 participants with mean loss of 6 pounds, and our standard deviation is 2 pounds. And then group 2 with diet 2 has 12 participants with mean loss of 4 pounds and standard deviation of 1.5 pounds. Assume normal distributions and equal variances, so keep that in mind. And then it says that our pooled standard deviation, SP, is approximately 1.74, and our standard error of the difference of means is approximately 0.75, and we're asked to find the test statistic. So if you recall from our formula sheet, we can see that when our variances are equal and we're looking for a difference in means, we can use this formula over here. And so let's just go back to our problem. So we have our test statistic T, which is equal to our x bar 1 minus our x bar 2 minus our difference of means, so that's mu1 minus mu2 divided by SP, and then 1 over n1 plus 1 over n2. And then recall that our standard error of the difference of means, when the variance is equal to this entire part down here, so it's SP times the square root of 1 over n1 plus 1 over n2, and so we can just use that, so that's 0.75, and then we have our x1 in our problem, so that's x1, and then this is x2, so these are our mean here, x2, and these are our sample means. And then since usually when we compare our null hypothesis is that they're equal, so this is just going to be 0. So now we can solve this. So we have x bar 1, so that's 6, minus x bar 2, which is 4, and then divided it by our standard error of difference of means 7.5, and they give us our pooled standard deviation, but we don't really need it since they already give us our standard error of the difference in means. And then this is 2 divided by 0.75, and that is equal to 2.67. And so that's really close to this number here, which is 2.68. And so that's our correct answer. And for our next problem, with our degrees of freedom is 20 and our critical value of 1.725 for the upper tail test at 5%, the conclusion is, okay, so we have our critical value over here, and then we can find our p-value from our critical value. So they said that it's an upper tail test, and then we're using 5%, so our alpha is 0.05, and then our p-value will be the probability if t is greater than 1.725, and we can look at our t-table for this. So and our degrees of freedom, as we recall, is 20. So we can look under 20, and then 1.725 is over here, and that's 0.05, as we can see up here, and we can go back. So then we say our p-value is 0.05, and since it's less than or equal to our significance value, which is also 0.5, so it's equal, we can still reject our null hypothesis, and then we can say that we have evidence that our diet 1 results in a greater weight loss than diet 2. So we can circle this one, and that's because our alternate hypothesis, since it says here, is since it's an upper tail test, we're looking for if our diet 1 is greater than diet 2. Okay, so studies suggest that playing video games may improve reaction time, and the average reaction time is 400 milliseconds, so a random sample of 12 gamers has a mean of 370 milliseconds and a standard deviation of 40 milliseconds. And to test that the gamers have lower mean reaction times at a 5% significant value, we need to find our t-statistic. So first let's find our hypotheses. So our null hypothesis is that mu is equal to 400, and then our alternate is that mu is less than 400. And now we can look for our t-statistic. So if we look over here, since they don't give us our standard deviation for our population, we can use this t-statistic formula over here. And so that is t is equal to x bar minus mu 0 divided by s divided by square root of n. And so we can look at these values in our problem. So we have this is n, this is our x bar, and this is our s. And so we can plug all of that in. So we have 370 minus, and then our mu 0 is 400, and then divided by 40 divided by our square root of n, which is 12. And then we can plug this all into our calculator, and we get negative 2.60, and we see that's this number over here. So our correct answer is A. And then, so if our p-value is approximately 0.013, this means, so our first answer choice says the probability of our null hypothesis is true is 0.013, and this sounds right because our 0.013 is the probability of seeing our results with the null hypothesis being true, but this isn't the actual probability of the null hypothesis being true. You can't really say that it's it has a probability of being true since it's either true or it's not. But so we can say that this answer choice is false. It is a little bit confusing with the wording, but it isn't the probability that it's true, it's only the probability of seeing our results while it's true. Okay, so then our second answer choice is the probability of observing a mean of 370 milliseconds or lower if our mean is 400, for a true mean 400, and then that is, the probability of that is 0.013, and so that's true because that's the probability of observing what we observed while our null hypothesis is true. So our correct answer should be B, and then it's not our power and it's not our probability of our type 2 error, so these two are wrong. Okay, so the next questions, a study of an automobile data in Indiana. So a random sample of 100 automobile owners in the state of Indiana show an automobile is driven an average of 23,500 kilometers per year with a standard deviation of 3,900 kilometers. And we assume that the distribution of measurements to be approximately normal. And so they want us to construct a 99% confidence interval for the average number of kilometers an automobile is driven annually in Indiana. And so we can look through our formula sheet. But first, let's see what values we have. So we have our n, and we have our x bar, our standard deviation for our sample, and we want to calculate a 99% confidence interval, so that's 1 minus 0.99, so that's 0.01 is our significance level for our average number of kilometers. So we can pull up our formula sheet, and we want to test for our confidence interval, and they aren't given the standard deviation of our population, only of our sample. So we can use this formula over here. So let's go back. And so that's going to be our x bar plus or minus our t alpha divided by 2 with our n minus 1 degrees of freedom times s over square root of n. So let's see what our degrees of freedom are. So that should be just n minus 1, and we see that our n is 100, so that is 99. And actually, since our n is so large, we actually don't even need to use our t-test. We can use our z-test. So we can assume that we know our standard deviation because our sample is so large. We can use our sample standard deviation to estimate our population standard deviation. So we can say this is about equal to that. And so we can actually use our known formula. So that is this over here. Which is really simple, except we use our population standard deviation, but we can say that they're about equal. So now we can find our z value. So it's our z of 0.005. And we can look at our table. And then, so since we're looking for the right side of the curve, we want to do 1 minus our 0.005. So that's 0.995. So we can look over here and see if we can find it. And so it's between these two values. So it's 2.575 around. And then we can plug all of this in. So we have 23,500 plus or minus our 2.575 times our 3,900 divided by square root of 100. And let's just calculate that. So 5 times 3 divided by square root of 100 is 10. And so that's equal to 23,500 plus or minus 1,004.25, and that gives us our confidence interval of 22,495.75 to 24,504.25. And we can compare our values here. So 22,495, so that's close to 494. And then this is also close over here, and so we can say that our answer is E. And then our next question says, what can we assert with a 99% confidence that about the possible size of our error if we estimate the average number of kilometers driven by car owners to be 23,500 kilometers per year? So we can assert that our error to be less than or equal to the value that we calculated. So we calculated that our error is around 1,004, and so we can say that our error is less than or equal to 1,004, so that would just be B. And then our last two questions. So a study investigates whether listening to classical music increases study efficiency by reducing the time needed to complete the task. And so 8 students were timed, completed the same study with and without music, and we have our differences. And then to test if music reduces study time, and that's like a positive mean difference at a 5% significance level, what are the null and alternate hypotheses? So we can just write that out right now. So our null hypothesis should be that our samples should be, or our mean difference should be equal to 0 if we want to say that our study time is equal for each. And then for our alternate hypothesis, we want to see if the music reduces our study time. So they say positive mean difference, and so that means it's just that our mean difference is going to be greater than 0. And then so we have 0 here, and then we have greater than, so our answer should be B. So they say the test statistic is approximately 2.26, and the critical value for degrees of freedom equals 7 at 5% is 1.89, and so what is the conclusion? So we don't even need to calculate anything since we already get our test statistic and our critical value. And so we can look at, we can either calculate our p-value with our test statistic or just compare the critical values. I prefer looking at the p-values usually, so we can do that first. But you can also solve it the other way. So our p-value is going to be equal to the probability that our test statistic, and then we can just look that since our sample is so small, we're probably using a t-test statistic. So we're looking for if t is greater than 2.26, and we can just look in our table with our that, and then we have our degrees of freedom is 7, as I said earlier, so we're looking for 2.26, and that should be between these two numbers, so a little less than 0.025, so it's between 0.025 and 0.05. So we have that it's less than our 5%, so it's less than our significance value, and so we can reject our null hypothesis, and then we are testing against our music reducing our study time. So that means a positive mean difference, and so our conclusion should be that we have evidence that music reduces study time. This is wrong because we are looking for if music reduces study time, not increases study time, and we also only have evidence that it is true. We don't say that it is true for sure. That's why we don't accept our alternate. We just say that we just have evidence that, so we say that our answer should be A. And that's the entire practice exam 1. I really hope this helped you prepare for your exams, and good luck. See you next time. Bye.